The way I would prefer to have questions, if you have a clarifying question, like you don't understand my axis of a graph or something, please butt in and ask that question. But I'd ask you to take notes and ask questions really about the progress of Superfund or groundwater or anything at the end of the talk, if that's all right. So I have worked in Superfund since 1990, both in Butte and Anaconda. I've been a hydrogeologist all that time. So I've looked at both groundwater and streams in both those places. So this is kind of putting together a lot of background information. So, let's see. Got to figure out how to advance this now. It's not advancing on your screen, is it? Oh, wait a minute.
I don't see it advancing yet.
There it advances.
Yes, now it advances.
Alicia, can you see my cursor, by the way?
Yes, I can.
Okay. So what we're really looking at is how does groundwater affect a stream? And so here we have a drawing of a stream, and we're going to call this a stream reach.
It
So
started already?
Reach, we could have groundwater either coming into the stream, and we can see over here that the water table slopes down into the creek. The other way this can work, though, is you can have the water table actually going that way. In other words, the stream would be providing water to the aquifer instead of the aquifer providing water to the stream. So I just want to get that clear. And as what we're going to look at is two ways of looking at this. And the first one is really how I started looking at groundwater, was putting in borings and monitor wells. And then you can sample the groundwater and figure out what the nature of the aquifer is. You can put in enough wells and measure water levels and start to determine a potentiometric surface, or so you can understand which way groundwater is flowing. And really importantly, and probably what's going on right here, is you can start to put together a stratigraphy of that aquifer. But the other way we're going to look at this, I'm having to advance in two places, is by measuring what's going on in a stream. So in this case, there's been, under Superfund, there's been a very intensive water quality sampling program. Monthly, they go out and measure water quality and flow at 7 different stations. So it's provided a heck of a database. And so here are the stations, and I hope you kind of orient yourself with this picture. Obviously, here's the Berkeley pit up here, and this is Montana Street coming down here. So between any two stations, that would define a reach, so we can look at the differences between those two stations. And if we're looking at flow, if there's an increase in flow, we can assume maybe that's groundwater coming in. Or if there's an increase in a contaminant, we might assume that that's a contamination input from the stream. So let's take a look in the past at what Silverbow Creek looked like and why we have this problem. So this is an area called Butte Reduction Works. This is the old stack at the Butte Reduction Works. You can see that the stream is actually flowing through tailings. You can just assume that underneath those tailings, there's an aquifer that's equally contaminated.
All you can do is rely on China.
Okay.
Hi, Joe. I muted everybody. Sorry. So you might want to
Okay.
repeat that last little bit. I apologize. Now you are unmuted and everybody else is muted.
Okay, thanks. So in 1987, this area was declared, Butte area was declared part of a Superfund site. And the red boundary is Butte Priority Soils Operable Unit. It's one of the operable units within the larger Superfund site. So a couple of things to look at here. The blue line is Blacktail Creek up until it meets that yellow line, and then it magically becomes Silverbow Creek. The yellow line starting all the way up in the Yankee Doodle tailings impoundment at the north end is the old flow channel of Silverbow Creek. The part where it enters within the boundary, the red boundary, is now called Metro Storm Drain. We'll get to that again. But keep in mind that it is EPA that oversees getting the work done right, and it's been Atlantic Richfield's dollars that have paid for pretty amazing data set, both groundwater and surface water. So here is looking at a 1995 picture of the area we're going to kind of focus in on. So we can see Blacktail Creek coming in here, and then it's called Silverbow Creek down here. This thing called MSD, that stands for the Metro Storm Drain Channel, and it is now underlain actually by a groundwater capture system. But if you went down there today, the only water you would ever see in the channel itself is stormwater coming off of the Butte Hill, and it's highly contaminated. That's a whole other story. So we're going to look at, this is what it looks like now today. Again, Blacktail Creek turning into Silverbow Creek. And we now have these two groundwater capture systems. There's the Metro Storm Drain subdrain, and there's the hydraulic control channel. Both of those are just, the MSD subdrain is a horizontal pipe with slots in it that collects groundwater. The hydraulic control channel is really an open channel that the bottom is below the top of the water table, so it's gathering storm water. I mean, it's gathering groundwater. So, we're going to look at both this system, we'll call it the MSD system. We're going to look at it first, and it's largely a groundwater story. Dang it. Then we're going to move on to lower area 1, which is the western portion of this. And there's been a lot of work done in that area, including this groundwater capture system, but they've removed an immense amount of tailings along the stream side, and they've entirely rebuilt Silverbow Creek in that area. So under EPA's requirements, they've said contaminated groundwater, if it keeps getting to Silverbow Creek, then Atlantic Richfield, you have to do additional groundwater control. And in part, what that really means is that you have to meet water quality standards in the stream. So here's our picture again. We can see both of the groundwater capture systems in yellow. We can see there's an area actually between those two capture systems with no control on groundwater. And then you can see the black outline that's kind of got a blue fill to it. That's called groundwater technical impracticability area. So EPA determined in that area they could never clean up groundwater. And so that's why they made the statement. Once they said they can't clean up that groundwater, it's technically impracticable from an engineering standpoint to ever meet groundwater standards. Then they had to say, well, how are we going to protect the creek? And so they made the statement I made before, is if groundwater contamination is affecting the stream, then you'll have to deal with that. So let's look at where we're at to date as far as water quality in the stream goes. So we've got two stations, one SSO1, which is located outside of what's considered the mining influenced area, and it's all the way up at Harrison Avenue. And then we have SSO7, which is located at the most downstream part of the Superfund operable unit. And it's right where Silverbow Creek passes under the interstate. So here's a history of water quality through 1993 up till 2019. Now I need to explain this. This is not total recoverable copper concentrations. This is a compliance ratio. And the reason we use the compliance ratio is it just naturally fits in, are you meeting water quality standards or not? And the water quality standard for aquatic life, water quality standard for copper is based on the hardness in the stream. So you collect a sample, you measure the amount of copper in it, you measure the hardness of that water, then you can calculate the standard for that day at that time. So if you just simply take the concentration and divide it by that standard, that moving standard number, you come up with a ratio. The ratio simply simplifies how you look at this, in that if it is above 1, you're exceeding the standard. If it's less than 1, you're meeting the standard. So we can see here back in 1997, we see these big spikes in total recoverable copper at the downstream site. That was when they were digging up the Colorado tailings downstream. We'll see that later, but that was a major removal right in the middle of the stream. Obviously, it caused big spikes. But after that, it started coming down. And we can't see on this scale whether we're at 1 or not. So let's focus in on this last part. So again, this is the compliance ratio. And now we can see upstream, or our background water quality at SSO1, and compare it to SSO7. You can see that there's definitely a gap still existing in what's picked up by the creek as it passes through the operable unit. You can see that we're still not meeting standards. Most of the spikes have occurred during high flow periods, during April, May, and June. But this one particular spike here was in October, and I'm not really sure what that's from, but that's not related to higher flow periods. One thing that you should note, and we'll look at this again later, is the difference in the gap here in 2016 and then looking at 2018. The difference there is simply that we upgraded our sewage treatment plant. And although that sewage treatment plant was intended, the upgrade was intended to remove nutrients, it also had a pretty big effect on removing copper. So as far as remedy measures goes, I think zinc tells a fairly different story in that it is now meeting standards, and it has been meeting standards since somewhere late 2005 or 2006. And it really corresponds to when they put in that metro storm drain subdrain. So that has been a very effective groundwater capture and treatment system. So let's look back again. It's good to always get a little bit of historic context. This is kind of that same layout. I think you recognize the pieces and parts, I hope. But we're going to talk about the Parrot smelter and the Parrot tailings, which are located in that left circle. And then we're going to look at the Butte reduction works. We're going to look at some really specific effects from both of those locations. And of course, the red outline up there is where the Berkeley pit will start to appear in 1955. So same picture again, sort of. And here are the two locations, and the yellow line there is again that subdrain. But in the case of this metro storm drain corridor, we're talking about a groundwater plume from those Parrot tailings, which I believe extends all the way to Blacktail Creek. That's always a matter of some discussion amongst hydrogeologists. But let's look at how the groundwater studies have gone to start with. So typical groundwater study is, and in this case, they were drilling with air, but they'll bore a hole, they'll look at what they drill up and kind of start to determine what the hydrostratigraphy is. They'll put in the well, and then again, they can measure water quality in the aquifer wherever the screen zone is, so at what depth that screen zone is. And then they can also measure water levels. So this is what one of the aquifer materials look like when we're drilling with air. This is pretty coarse. This is at the upper end of sand size, or maybe very fine pebble size, but this is a very good aquifer material. You could really push water through this pretty well. So here's another way to drill, and these are split spoons. You can see up here a sandy section, but then right here you can see a very tight clay section. So this would be aquifer material. This would be what we call an aquitard. In other words, water really doesn't flow through it, and it can separate those aquifer materials into unique aquifer units. And just a picture of a well screen. So this, that's the area where you would actually pull water in to the well from the aquifer. So again, we're back at, this was sonic drilling. It created a continuous core, and the core came out wrapped in those plastic casings. Unlike the drilling with air, you could get a really good view of what the stratigraphy looked like. So right here, we're talking about a nice sand zone. You can see how it just fell apart. And right here, we're talking probably pretty clayey material. Again, that's just a close-up of the same thing. So then the hydrogeologist will start to put this together and put together these well logs. And in this case, here's the description. Here's a lithologic log. In other words, it's symbols of different things like sand and gravel, and this is silty sand. But over here, they had actually collected from the cuttings, or from those cores, they had actually done XRF concentrations in the solid media of these constituents up here. And again, here's the screen zone, so you can match up where they've screened it with what the lithology was. So then you try to piece this together. Here's all of the wells. I think this is all of the wells that are out there right now. It's quite a few. They've been put in different eras of drilling and trying to characterize this aquifer, but it's quite a few wells. So then we get to trying to build this hydrostratigraphy and understand how groundwater flows and how contaminants are transported. And what comes to my mind is the old story about the blind men trying to describe an elephant. And so this guy here feeling the tusk says it looks like a spear. This guy feeling the leg says, you know, I think it looks more like a tree trunk. And this guy here, he says, I think it's a rope. So this is Montana Bureau of Mines geology of the interpretation of the stratigraphy at that point. This is in, I think they did this one in probably 2012 or 13. So they definitely are lumpers. So they've taken a lot of different stuff and they try to put it together. And so here's an overall look at what they think the aquifer, how it behaves. So here you have the surface aquifer, or the shallow aquifer, sorry, the middle alluvial aquifer, and the deep alluvial aquifer. And then it's divided by clayey or silty aquitards in between, the brown layers. So here's the lithology over here. So up here is GS41 S&D. It is right at the heart of the Parrot tailings. It is the most contaminated aquifer. As far as copper goes, I'm sure it's the most contaminated aquifer anywhere. But by contrast, and I'll just add in, this is probably, as a hydrogeologist, where I fit into the discussion is, I guess I'm a lumper. But here's the splitters, and this was done by Atlantic Richfield's contractors. Again, I have a circle around where the Parrot is, and well, GS41. In this view, one important part is they have the bedrock surface in here, and although they only have one well that intersects it here and one well over here, so most of this is made up along here. All of us hydrogeologists agree that it shallows as you move towards the west. That's one thing we've all agreed on. But let's close in on that a little bit. And so they've just taken where they measured sand, or sand and silt, or sand and gravels, or silt and clay, and then they've turned that into very fine units in some cases, like right here. That's a bunch of different units. Here's where they tried to run the middle alluvial unit through here, and it's hard to agree that that's what it is. But this is another way to look at it. It's certainly a more detailed look at what an aquifer looks like, what the hydrostratigraphy looks like. So now let's look at a cross section, looking at water quality and see what we're really talking about. Because the only reason we're doing this is because there's a contaminant plume. So again, here we have the Parrot tailings up here, and that's the head end of the plume. So notice we have a log scale. This is concentrations, and this is zinc and copper. Copper's in blue and zinc's in orangish color. But notice this is on a logarithmic scale. So this is over roughly a mile distance. We start out with copper at the Parrot at being 1 million parts per billion. kind of pretty concentrated anyways. And we can see that it's dropping by orders of magnitude. Here, right at the edge of Blacktail Creek, copper's gone down to about 3. Zinc's still way up there at probably 50. But another important factor to understand is that a lot of this is controlled by the pH of the water in the aquifer. So starting at the Parrot tailings again, at GS 41, we have a pH that's about 3.7, 3.8, so pretty acidic. It also means that copper and zinc will stay in solution pretty readily. By the time we get down to Blacktail Creek at AMW 13B2, we're all the way up at fairly neutral water. So, like I said, we can put together water levels using a lot of wells and come up with a potentiometric surface map, which will tell us which directions groundwater is flowing. And there's been a lot of controversy over that, but one of the things I'm pretty sure of is that in this region, you start to develop a groundwater divide. And so you probably have water that's being affected by the subdrain and is actually, there'd be a lot of flow lines that are headed straight into the subdrain. At least the aquifer very close to the subdrain, it's all going to the subdrain. But there seems to be another flow path that would come down here and intersect Blacktail Creek. So now let's go back to our monthly synoptic sampling and see what Silverbow and Blacktail Creek will tell us. So now we're going to look at SSO1 and SSO4. Well, actually, I was supposed to take that slide out, sorry. We're going to look at SSO1, SSO4, and SSO5. And so we have 2 reaches now. There's the Blacktail Creek reach, and then there's the confluence reach. So now this is going to take a little description, but this is putting together data through that time period from January 2015 till the end of 2018. What I've simply done is between any 2 of those stations, say SS1 and SS4, I'll take the concentration of copper at SSO4 and subtract off the concentration at SSO1. So if there was an increase in copper in the stream in that reach, it would be a positive number. So do the same thing for that downstream reach, the confluence reach, but then you take each of those monthly gains or losses and you start to just add them sequentially. So it's accumulation of whether it's gaining or losing. And the importance of that is if it's tending to lose concentration for some reason, then these slopes will be negative. If it's always gaining, then the slope will always be positive. I hope that makes sense. That's kind of a lot to describe. But I want to draw your attention to this short period of time here. And we can see that there's a big step up right at that location. I mean, right at that period of time that corresponds to work they were doing at the end of the subdrain where the pump vault is. So they were there, it was an operational change for a short period of time. They're actually putting in a second discharge line that would take that captured contaminated groundwater down to the treatment system. I don't know exactly what they had to do operationally, but it affected water quality in Blacktail Creek, which is really upstream and in the reach of under the influence of this portion. And in the confluence reach, we see the same thing, but I'll go back a slide. And after they've finished this perturbation in the system, you'll see that at Blacktail Creek, we continue to have a rising cumulative copper. And in the confluence reach, it is flattened out, which means that subdrain really is effective. It's just not capturing this portion. So that was talking about that little portion, the eastern half of the domain that I'm talking about today. That's really about a groundwater study and then how a stream study works. The only work that's been done in that area really is to put in that subdrain and capture groundwater. Now we're going to move to the western portion, and this area is called Lower Area 1, or LAO. And there's been a lot of work done here. So it looked like this. And it looked like that. Hang on. But in this area, they have removed 1 million cubic yards of in-stream tailings. They have rebuilt the floodplain and stream. They have put in a groundwater capture system. And then they've built a groundwater treatment system. So we'll get to a little more of that in a minute. But first of all, one of the things that we did way in the past, actually, Atlantic Richfield did this way in the past. This was a loading analysis before any of that removal was done. And in this loading analysis is what we're going to look at is if you take measurements at all of these stations on the creek, Silverbow Creek in, Missoula Gulch was a stream that flows in. Here's the sewage treatment plant. It discharges into the creek. And then we have Silverbow Creek out. So we're going to measure both zinc concentrations and flow at those stations. Then we can simply multiply flow times the concentration, and we'll come up with a load. In this case where I said cubic feet per second times milligrams per liter, we would come up with milligrams per second, but in the usual term used is pounds per day. So here's how you put it together. You have to use your conversion factors, but they measure flow at Silverbow Creek at Montana, then Missoula Gulch in, and the sewage treatment plant in, and then Silverbow Creek out. So now what we're going to do down here is start with Silverbow Creek out, subtract off the flow here, subtract off the flow here, subtract off the flow here, and we can see that probably our increase, what's left over is 1.6 cubic feet per second of groundwater inflow. So we're going to do the same thing over here with load, and we're going to start with Silverbow Creek out. We're going to subtract off the sewage treatment effluent, Missoula Gulch in, and Silverbow Creek at Montana, and we end up with an inflow load of 330 milligrams per second. Is what that's telling us is that the groundwater load at Silverbow Creek at I-90, 72% of that load has come out of groundwater in that reach. That's about a 1 mile reach. So it was significant. So here's what the area looked like. The light blue line is where the creek runs today. The yellow line is where it was running at this time in the past. This is the Colorado tailings right here. So here's what we have today. And here's the old Silverbow Creek line, the yellow line. Here's where it is today. So let me describe what else you're seeing here. They've rebuilt this floodplain. remember they've removed over 1 million cubic yards of tailings. Now they've built a water treatment facility, groundwater treatment facility. It's just simple lime addition. So lime's added in these first basins. They're light blue because they're precipitating out metal hydroxides, and it's scattering light and it looks light blue. The discharge from this system is down here back into Silver Bow Creek, and that discharge meets water quality standards pretty well. Another thing I'll point out here is this is our sewage treatment plant. Yeah, like I said, those are called the Butte treatment lagoons. The other thing they've done is they've put in this hydraulic control channel. It's just an open channel, but it sits down into the water table. So it's capturing groundwater that's coming from the north. There's another groundwater problem though. You remember when I showed the picture of the Butte reduction works from the past, and I said there's a highly contaminated groundwater aquifer under this. That's still there, and that's pretty much the groundwater flow from that aquifer. It's flowing along the axis of the stream, and that's still highly contaminated. But as what they've done when they rebuilt this floodplain from here up to about here, is they elevated the floodplain. So they engineered a distance between the aquifer and the stream. So now the stream is perched above the aquifer. So we're going to look at how well that worked too. So now we're going to go back. Now we're looking at some different reaches. So we've got the Slag Canyon reach, the Butte Reduction Works reach, Lower Area 1 reach, and the Sewage Treatment Plant reach. So here's our monthly synoptics, and this is the cumulative reach gain loss of total recoverable copper. Now we can kind of compare and see where the places we should be focusing on. Obviously, the sewage treatment plant would have been a good place to focus up until 2016. And then it doesn't seem to be a problem anymore. It's now even got a negative slope. So again, here's our sewage treatment plant, and here's where that sewage treatment plant discharges to the stream. It's in between 7 and 6G. That's called my sewage treatment plant reach. So we know that's been taken care of. So now let's go to the next worst groundwater problem, and that's called the Butte Reduction Works reach. And let's talk about it a little bit. So we're going to focus on this one little area there. Something's going on there. And then after that, we can see that there's a pretty even and continuous supply of groundwater copper still getting to the creek. So here's the reach we're talking about roughly. And when I said they rebuilt the floodplain and they elevated above the aquifer, that didn't start right at the top of this area. It couldn't start until down a ways. I guess they could have built a step in up here, but you could imagine from this end to this end, the separation of the stream from the aquifer would look like a wedge, like a thickening wedge, thickening from east to west. So this part was kind of left out of that engineering portion. So now we're going to take a look at one key photo I took in the past from right there. And that was, they had a track hoe out there digging in these tailings. So this gray stuff here is tailings. This is slag. But he was digging a hole down through the tailings, and he got to the water table, pulled up his bucket, and his bucket is, his teeth on his bucket are actually coated in copper. So the same thing happens up at the Parrot tailings. If you take some of the water out of GS41, you can plate copper out of it. There's so much copper, it will plate on any iron surface. So what's going on there? Well, we're going to tell a little story here, and this is really only a piece of the story, but I thought it was an interesting piece of the story. So we have our little maverick engineer, and he went to work there in that same area and built this little dam. And so here's the picture of it. There's where the dam was. And here's where my backhoe was. So here's where they've removed the dam. And I want to just show you a simple thing to note. Right here is a wetlands that was forming. So the dam was right there and water was just starting to spill on and across this whole floodplain area, generally running back off into here. But in this picture, after they removed the dam, it's no longer an active wetland. It had changed. But behind that dam, this is Silverbow Creek, which would normally look like a fairly narrow stream. There was a pretty big pooled area. So what that was doing, and I didn't illustrate this actually, is what that was doing was pooling water on top of that contaminated groundwater. There had been some studies in the past in that very area. We all knew that there was a seep that came into the bottom of the stream in that area that they measured. They could just take a bottle and stick it down into the bottom of the creek and capture water popping out of the stream bed and sample it or run it to the lab and analyze it. It was really high in copper. So we knew we had this seep coming in. Atlantic Richfield tried some little experiments where at the time downstream about where the beaver dam was, there were a series of culverts, and those culverts would get dammed up with debris, shopping carts and discarded whatever, basketballs and everything. And so it was dammed up with trash. So we raised the head of the stream above the aquifer, and at the same time, they pumped the local groundwater there to lower the water table. And they found that in that area, the copper in the stream was very sensitive to the distance between the water table and the stream. So in this case, is what the beaver did was he raised stage of the stream, and so he was keeping groundwater from entering the stream at that time. Once the dam is removed, that groundwater starts to enter again. So the good part of this story is that this has been kind of a long road. And right now the EPA is moving forward with final parts to their remedy. And fortunately, they are now addressing those two main contamination areas. And they have specifically said that if groundwater contamination is affecting Silverbow Creek, and it is, or Blacktail Creek, then there will have to be more groundwater capture. In the Butte Reduction Works area, they're actually going to realign the creek and bring it down through here and add some groundwater capture. There's on the table some additional groundwater capture somewhere down in here. But the best part of this story, even to date, is that we do have fish back in this creek. For a long time, this was an absolutely dead stream. And we now, I don't remember when we took this, but this was probably in 2012, 13, 14, 15. Fish, Wildlife and Parks does fish surveys all along Silverbow Creek. This was one day in lower area 1, and this is a brook trout, so he was probably coming from upstream on Blacktail Creek, but pretty nice size brookie if you're a fisherman. This is a great size brookie. Those are Trevor Selch's hands. He's a fish biologist with Fish, Wildlife, and Parks. So at that, I guess if there are questions, go ahead and unmute and you can ask me. This is both myself on the right and Patty Kineen on the left at GS41, and the blue water in the bucket, it's blue because of the amount of dissolved copper in it. So any questions?
Great, thank you, Joe. So please unmute yourself and ask Joe questions.
Joe, can you hear me?
Yes, I can.
Yeah, this is Doug Coe.
Hi, Doug.
Hi. So can you sort of explain the difference between total recoverable copper and, say, total dissolved copper?
Sure, I can. And to start out with your question, Doug, in groundwater, we just measure it as dissolved because we're assuming it is just dissolved moving through an aquifer. It's got to move through small spaces. And in stream, the current water quality standard is the state's total recoverable standard. It is a measure, it is an unfiltered sample. So it combines copper that is adsorbed onto particles, and it also includes dissolved. And Doug's question really gets at a big question, in that the state uses total recoverable as a standard. The EPA uses the federal standard, which is simply dissolved or a filtered sample. And there's generally a pretty big difference between the two in stream. But EPA also went on to say that they chose, when they were choosing standards that had to be met, they chose the state standards. And at this point in time, as they're trying to move forward with final decisions, and they will be waiving during stormwater 2 copper and zinc total recoverable standard to the federal dissolved standard. During normal flow conditions, they're not waiving any standards in stream, but there are provisions in what's written up now that they may do that in the future. I hope that answered your question, Doug.
Yeah, I did. Thanks.
I guess Bev's not on. There'd definitely be a question.
I see Fred on there, so maybe, yeah.
We actually are both here, but I thought we should have the students asking questions.
Okay.
Are there any student questions for Joe?
Let me ask this question to you guys or somebody. Was that a lot to take in?
It wasn't bad.
Good. We have a lot of biochemists on the line right here. So
Yeah. So I thought it was really good. The question is, are some of those graphics available, other than, you know, the ephemeral thing or screen capturing while you were talking?
Oh, I'll provide the PowerPoint if you want it, Bev, or to anybody who wants it.
I think, yeah, that would be great for the class to see that too, Joe, if you don't mind.
Yeah, I'll have to, I'll either have to give you a thumb drive. It's like 100 megs. So I'll have to either give you a thumb drive or, you know, some kind of sharing.
Okay.
I can't email it.
Obviously. So I have a question. So for those reaches where you showed that there's continuing addition of copper in those areas, is anything being done, like what happened with the sewage treatment plant, to flatten that out so that's not happening anymore?
Yes, and under the proposed plan, it's simply left at additional groundwater controls. So what exactly will be done is left to the future. But it's pretty clear that groundwater controls can do a heck of a lot. And you know, it is all relative. So, you know, the relative positive rise in those cumulative plots relative to each other, you know, some of them are barely sloping upwards. Some point you get to the point where you're trying to do a lot of stuff and you're not going to have much effect. But I think for the two areas I showed that there was still this concern, both there in lower Blacktail Creek and then at the Butte Reduction Works area. Those are focus areas. I'm not sure exactly what they're going to end up doing. You know, they could do removing some of those tailings. They could put in additional, another subdrain or more hydraulic control channel, or they could put in wells and just pump that groundwater. So that's kind of left up to Atlantic Richfield to come up with a plan, and it's up to EPA with the support of DEQ to be satisfied that they're doing enough.
So I have another question that relates to what's going on with the parent tailings. What major differences do you think is going to happen after the parent tailings removal is complete in terms of what you were talking about, you know, for all these reaches, those two stretches? Will that improve what's happening in the BSB part because you think it's leaking off of the Silverbow Creek groundwater area plume dividing?
That's a big and very loaded question, but I'll answer it. When the EPA wrote their record of decision in 2006, Montana Department of Environmental Quality had a letter of partial concurrence attached to that. And in it, they said they agree with most of the remedy, but they had a real problem with the groundwater portion, and especially leaving sources of major groundwater contamination in place, like the Parrot. And the way the DEQ was looking at it at the time was not that we would clean up the aquifer. We sort of agreed that you're not going to clean up the aquifer, but we thought that as long as you leave the source in place, the plume can continue to expand. And so you might see additional increasing contamination in Blacktail Creek. And that was our major concern back then. That's still the major concern at present in my mind. And it's a reason why the state, rather than ARCO, is digging up the Parrot. But I would also say I have little expectation that this aquifer will clean up in any amount of time. But again, that gets back to how many hydrogeologists can dance on the head of a pin. But from my experience, it would probably be more in the range of hundreds to thousands of years to have that aquifer cleaned up to the point where you could just release the water into Blacktail and Silverbow Creek without treatment and capture.
Yeah, so what if you, after you took the Parrot tailings out, then you put a few big pumps in there that caused the groundwater to move backward and then pumped basically the water either up to Arco so they could take the copper out or into the Berkeley pit or something. I would think that would speed up the aquifer cleaning itself up.
It would be better control on the plume. The trouble with the aquifer is that it is the fact that you had contaminated groundwater, especially this middle alluvial unit is at roughly 40 to 60 feet in depth, poorly defined, but there's a lot of fine-grained portions to that middle alluvial unit. And it is that groundwater, dissolved copper, say, in the groundwater is moving through that aquifer, and it's starting to load up those sediments. And especially the more fine sediments you load up, the more you end up with a solid phase in the aquifer. So the problem is that as you do slowly clean up the aquifer, you're very slowly starting to remove what is now a secondary source of copper off the solid aquifer material. And that's the part, you know, you can I used to subscribe to a journal called Groundwater, and I don't remember how far back that was. It was a long time ago, probably in the early 2000s or something. There was an article called The Black Swan, and it was an editorial from a hydrogeologist from one of the publishers saying, we've been doing a lot of work now for 20, 30 years on aquifers, trying to clean them up. And the experience is waiting to see if they clean up is like waiting for a black swan to arrive. So I'd say based on, I don't know if it's a general consensus among hydrogeologists, but it's general consensus among a lot of contaminant hydrogeologists that aquifers don't clean up very well.
So thank you. I don't know how long this goes on, but I really think the students ought to be asking questions.
Well, like I said, I think it was a lot to take in.
Are you available for people to email you questions or email Alicia questions to pass on to you?
Yeah, sure. Oh, absolutely. Always.
And Bev, we discussed Joe's talk as a class on Friday together. So we'll talk about it. And if we have more questions, we'll get a hold of Joe.
Oh,
Yeah,
good.
that'd be a good way to do it, is after discussing. And like I say, I'll get you the PowerPoint, so maybe you can put it up in your discussion and look at any slides you want, Alicia.
Yeah, that sounds great. Yeah.
Okay.
Hey, Joe, I have a different kind of question.
Okay.
What's it like to give one of these talks to an essentially empty room?
That's a great question because all of our students are going to give their talks over Zoom. So please let us know.
Well, I guess the problem, you know, what I just found out is I don't talk with my hands when I'm just talking to a computer screen. When I'm up in front of an audience, I think I wave my hands around a lot. I don't know. It's not bad.
You know, I'll make a comment on having sat through your talk here, and it's the best graphics I've ever seen. Okay, in terms of my being able to see them. Hearing you was absolutely fine. Being able to listen to the discussion went really well as well. You know, I would almost prefer, except for the social interaction with people, I'd almost prefer this format.
So another comment, you know, if you have the participants, the little thumbnail of their pictures, either live or just, you know, still pictures that are there representing them and their names, that gives us, I mean, I've been in other meetings, that gives a sense of participation and having audience more than just what we're looking at here, which is only you and none of the other 18 audience members.
I'll tell you one thing, Doug. When I was pausing and there was sort of dead air for moments, I have two screens up, and one is the one that you guys are seeing, and one is you know, all of my slides, so I could kind of see what's coming next. And I was having trouble getting it to operate on both screens right. So then I was going back. Yeah. Anyways. So if you're asking for a suggestion, it's make sure you know how all of this operates.
It looked pretty flawless from this end.
Oh, thanks.
So
I agree with Doug. It just seems excellent.
This started out as being my presentation. It was going to be a 15-minute presentation to the American Water Resources Association in Red Lodge, and I ended up with the flu and didn't go. So this was expanding a 15-minute talk to 50 minutes.
Gretchen, you've unmuted. Do you have a question?
yeah, I was going to ask about if there was an array of pump wells, but that's kind of been answered. My understanding is that there's not really an array of pump wells. How well is the plume mapped out and monitored?
You know, that goes back to my blind man trying to describe an elephant. Is it's really hard. And you know, being in discussions trying to decide whether there's going to be more wells or less wells. Of course, I'm a hydrogeologist, and so I always wanted more wells, and the people paying for it were generally saying, we've already got 212 wells out there, why would we need more? But it's like, well, it's just, I can tell you where I want some more wells. But you know, and I shouldn't just say that, because it possibly reflects poorly on Atlantic Richfield. And I'll tell you, they came along and said, we really want to figure this out. We're tired of beating around the bush. And EPA had come up with a plan to install, and I don't have the numbers right, I'm going to lie to you a little bit, but say 13 additional wells, and Atlantic Richfield came back and said, yeah, we'll do those. And then we're going to add 20 wells to that. So it's a great question. I would say, in my mind, I kind of understand it, but when you're trying to do potentiometric surface maps, there's too much room to push the interpretation one way or the other. Mm-hmm. And getting back to, you know, they did, the north half of the parrot tailings were removed in 2018, and they put in a pumping system, and they've been pumping that water back to the Berkeley pit. And I'm not sure, there's been some discussion that they could continue on with that. Nobody really knows where that will go, but that's the only groundwater pumping that I know of.
Okay, thank you.
Yeah, I had kind of a related question. Have there been any tracer studies, or even slug tests or anything to look for further characterizing some of these units? It looks very heterogeneous.
That's a great question. So when there was something called the focused feasibility study, and it focused on just this question, the parrot tailings and the aquifer. And in it, they characterized the aquifer as heterogeneous. And they said it can be characterized as having a hydraulic conductivity of 3 feet per day. And this was back in 2005, before we had the record of decision. And DEQ was actually given some money to give to the Bureau to drill a couple of additional wells. One of them was up by the Parrot, and they put in a well that would act as a pumping well. And when we drilled that well, some of us hydrogeologists were looking at it and we're going, well, down there, like 40, 50, 60 feet, it looks like really sand and gravel. And we thought, well, that's not 3 feet per day material, that's hundreds of feet per day material. And so we got language in EPA's record of decision that said they would run a pumping test at that location. And in the past, they had done a couple of very short pumping tests and some slug tests. So they ended up, after the record of decision, they ended up pumping that well. And if you know the Civic Center and you know the locomotive, the well is right next to the locomotive, and it's like 200, 300 yards down gradient of the Parrot. So they pumped, it was a 72-hour pumping test, good test. And they had to, this water was so contaminated, they had to put it in tank trucks and take it down to the Butte treatment lagoons for treatment. But they about 10 hours into it, the fittings in the piping for the pumping test started leaking. So they had to shut down the pump test for a short while. And as what it was the iron in the fittings was being replaced by copper, and the copper was soft enough that the fittings weren't holding together, starting to spring leaks. So there was so much copper in the water that it was plating out on the fittings. Anyways, long story short, Atlantic Richfields Consultants did aquifer analysis. The Bureau did their own aquifer analysis. We all agree, you measure a transmissivity, but we all came up with then converting that into a hydraulic conductivity of somewhere between 300 and 1,000 feet per day. So EPA's initial characterization of heterogeneous and very low conductivity, the heterogeneity, I don't know what you say about it. Every aquifer's heterogeneous, and so it's a matter of a shade of gray, right? And in the end, I guess I thought, after seeing the sonic drilling, my idea was it was much more heterogeneous than I thought when we were drilling with air. And we're getting really just cut up samples, and it looked a lot sandier and gravelier. But the hydraulic conductivity going from 3 to say 600 was a big deal. And as we put in more wells, we could also see there was definitely a continuous plume from the Parrot that goes down kind of the axis of that metro stern drain corridor of a plume. So the middle alluvial unit has a continuous plume. The upper alluvial unit is got a spotty plume. So some places it's a lot less concentrated and then downstream it might be more concentrated again. So the plumes in the upper alluvial unit are driven by overlying contamination, not the Parrot way upstream. That was a long answer.
Thanks a lot. That was a great answer.
Excellent. Are there any other questions for Joe? If not, well, we can't really do a round of applause when everybody's muted, but thank you, Joe, very much for that. And I will stay online to speak with the students. But first, if anyone has a question, please pop up.
I got a comment. This is Gary Eichbeany. Can you guys hear me?
Yes,
Yeah.
we can.
Yeah.
I just wanted to comment on your, Joe, your assessment that it'll take thousands of years for the aquifer to clean up. And I guess I agree that I don't think the aquifer will ever clean up, but I think the groundwater based on what we've seen around the Parrot and other places in the Butte Valley, that the groundwater will clean up fairly quickly. I mean, by that I mean the metal concentrations will drop out as soon as you remove the sources of acid. And we've seen that in other places, and it was in Nick and I's report. That said, I think that's true, and the reason I'm making the comment is sort of a biogeochemistry, something that maybe Alicia can talk about with her students, is that's true unless the water features they put in along that over top of that aquifer don't add a bunch of organic carbon to the aquifer, which has very little, which could, you know, drive things anoxic and then release a ton of metals. So all things being equal the way it is now, if you just remove the acid sources of acid, the metals will stop moving in the aquifer, in my opinion. And I think that'll clean up fairly quickly.
And I should explain to everybody that Gary's one of those hydrogeologists that's been dancing on the head of a pin with me since quite a long while ago. So, and you know, as I showed Gary, I mean, the pH of the aquifer, the pH of the water in the aquifer is a critical part of the story. There's no doubt about it. So.
Yeah, no, I agree that the aquifer will never clean up, but I think the metals will stop moving if you remove the sources of acid. But
Okay, thank you, everybody, for your comments, and thank you very much, Joe, for the talk. And I will stay online to chat with any students that want to talk. If not, I'll see the students on Friday over Zoom. Okay, thank you very much, everyone.
Yeah, give me a call, Alicia, and I'll figure out how to get you the PowerPoint.
Okay, yeah, sounds good. I'm going to figure out how to not mess up the recording too. So.
Okay.